Okay, so let's continue with the introduction to the course. We finished the first lecture by looking at some of the fluid properties that are going to be important for us. We discussed density, specific volume, specific weight, specific gravity. We discussed some of the concepts from equilibrium thermodynamics, including the ideal gas law. But today, we're going to start by discussing a very important property for us in fluid mechanics, which is the property of viscosity. And you are already familiar with the concept of viscosity by just everyday experience. But let me show you a quick video to see the difference that different values of viscosity can produce in fluid flows. So what you have here is two vessels with two fluids that have different viscosity. They actually have very similar density. One of them is water, the one that we will see first. So if you take water, you're all familiar with how water behaves. The other one is actually silicone, which has a much higher viscosity than the viscosity of water. Again, keep in mind they have the same density. So the density is not the issue. The density is about the same. What is making the second fluid, the silicone, flow in a much slower way is the fact that it has a much higher viscosity. So let's talk about viscosity. And the first concept that I want to bring to your attention is the concept of the no-slip condition. So let me go back to the document camera. And we're going to be talking about viscosity. And the first item is the notion of what is known as the no-slip condition. The no-slip condition, and I'll show you another video so you can see what it is. Let's go back to the computer. And let's go to the next video. What you have here, let me start this again. Let me pause it for a second. What you have is you can barely see, but at the bottom, there is a flat surface. And that vertical line that you see there is a probe that can inject a gas anywhere into the fluid. So by raising or lowering that bar, we can inject gas at different places in the fluid. And because the gas will follow the fluid in the field, it will be able to tell you what the fluid is doing. So right now, the probe is at the very bottom, so it's very close to the bottom wall. And when you release the marker gas, you can see how it actually stays stuck to the plate. It doesn't move from the bottom of the plate. There is a portion of the fluid that does travel away because of the gas, because it rises a little bit and it catches up with the fluid that is able to move because it's not stuck to the wall. And you can see how as we raise the probe, we can see how the marker fluid flows freely. But you can still see how at the bottom, the fluid seems to be stuck. The marker fluid seems to be stuck to the wall. So only when we brush it away, we're able to move it away. So that shows you the concept of the no-slip condition, because what is happening indeed is that if we draw a schematic of that experiment, if this is the bottom plate, what we see in this case, for example, the fluid was moving from right to left, but let's say that it's moving from left to right. So if this fluid is moving, oh, I'm sorry, from left to right. Let's go back there. If this fluid is moving from left to right, here's the wall. And we try to make a representation of how the fluid is moving. Then we saw that away from the wall, the fluid was moving with a significant velocity. But as we get closer to the bottom wall, that velocity was lower. And in fact, if we measured right at the wall itself, we would see that the fluid is not moving. So that's what we know as the no-slip condition. And it's really a result of thermodynamics. It's a result of the fluid that is in contact with the wall being in equilibrium with that wall. So on average, the fluid is not moving because the wall is not moving. But let's talk a little bit more about viscosity. So suppose I do this experiment. I'm going to change it a little bit by adding a second wall. So I'm going to put a second flat surface on top that is parallel to the first one. So I actually build a channel between these two parallel plates. I will keep the bottom plate fixed, but what I will do is I will be moving the top plate with a certain velocity. Let's call it capital U. And that velocity will be constant. So I'm just going to move it with a constant velocity, and of course, the way I would have to do that is by applying a force. So let's say that I'm applying a force to the upper plate in the horizontal direction. I'm pulling that plate, and that generates that constant velocity. And of course, the reason the velocity is constant, even though I'm applying a force, is because there'll be a resistance from the fluid that is filling the gap that will be resisting that motion. But I can leave my arrows there representing the way the fluid is moving. We refer to this type of a drawing as a velocity profile. So I'm just profiling the velocity at different locations from the bottom wall to the top wall. And of course, I could add the velocity of the top wall, which is the constant velocity u, as my uppermost velocity there. So I will have a profile there. So let's say that I do that, but let's just focus on what happens on an infinitesimal amount of time. So if I just concentrate on what is occurring in a small delta t, then I can say that the upper plate will displace, in that small delta t, the upper plate will displace a distance which is simply, of course, u dt in a small time, delta t. So this is the displacement of the upper plate. And then I can measure this angle. So let me do a drawing here, since this is all crowded with the arrows. Let me do another one here. So in that delta t, I can say that the upper plate displaced a certain dx, and I can measure this angle here, and let's call that angle d beta, the angle that has been swept by the line that goes from the bottom plate to the top plate. So I can write, of course, that the tangent of d beta is opposite sides over adjacent side. Let's say that this distance that separates the plate is also given to us, and let's say that that distance is h. So dx over h will be the tangent of d beta. But because this is a small angle, since only a small amount of time was considered, the tangent of d beta is, of course, for a small angle, very close to the angle itself. So tangent of beta can be approximated as just d beta, and that's dx over h. So if I now look at the time variation, so if I just take now the time variation of beta by dividing by dt, then what I have, of course, is 1 over h dx dt. And of course, dx dt, since dx was the displacement of the horizontal plate, we in fact see it right here. Dx over dt is just the velocity of the top plate. So this is simply u over h. So the rate at which the angle is changing is simply the ratio of the velocity of the plate to the vertical distance, the vertical gap between the plates. Now, of course, I can approximate that to the derivative of the profile. If I were to join all of these points with a line and make an approximation that that is linear, I could also say that this is a good approximation to the derivative of the velocity in the vertical direction. So if I say that I am measuring the y coordinate from the bottom up, so this is y, and then lowercase u is the velocity at that point, the fluid velocity at that point, then an approximation to the derivative, of course, would be the value of the velocity at the top plate divided by the gap. So I can say that that's du dy. And this is an important quantity in fluid mechanics because this is what we denote as the shear strain rate. So let me write that here. The variation of that angle with respect to time gives me a measure of how the fluid is being strained in time by this shearing force that is produced by the force that I am exerting on the top plate. So I'm shearing the fluid by moving the plate horizontally, and I can measure that rate of shear strain by this, which is evaluated by the variation of the angle, can be evaluated by the velocity gradient in the vertical direction. And what units does it have? Well, it obviously has units of, if we write the units here, velocity meter per second and the vertical gap in meters. Then, of course, the units of the shear strain are units of 1 over second. Okay, so now what we want to do next is make a connection between this shear strain rate and the force that is causing that shear strain rate. So think about, I know that the force that I applied at the top plate is what resulted in that shear strain rate. So I want to make a connection between the force and the quantity that I just wrote, the derivative of the horizontal velocity with respect to the vertical distance. However, what we do is, instead of relating it to the force, we relate it to the shear stress. So we define the shear stress as the force per unit area. What unit area is that? Well, that's the area of the plate, for example. So if I were to repeat this drawing in 3 dimensions, what I would see is that I have a plate at the top like that. I have another plate at the bottom that looks like that. And I am moving the top plate with a certain force. And when we talk about the shear stress, we would be talking about the force per unit area of that plate. And then that's the shear stress, and we denote that as tau. So the shear stress or the force per unit area is tau. And then what we want to do is we want to find what is the relationship between the shear stress tau and the shear strain rate du dy. That's a crucial question in fluid mechanics. That relationship between stress and strain rate. And it so happens that there is a particular type of fluid for which this relationship is linear. So, which means the following, that the relationship would be linearly proportional relationship. So if tau happens to be equal to a constant times du dy, then we call this type of a fluid a Newtonian fluid. When that relationship is linear. And the constant of proportionality, you might be guessing, is precisely what we call the viscosity. So that constant C that we get there, that connects the shear stress to the shear strain rate, is the so-called viscosity. And in fact, we don't use C for it, we use the Greek letter mu to denote it. So for a Newtonian fluid then, the important relationship is that mu is the constant of proportionality between the shear stress and the shear strain rate. Now, admittedly, this was a very simple experiment because we were simply looking at one type of deformation. We had the fluid between two parallel plates and we were moving one of the plates. So we really constrained the problem to this very simple geometry. If we were dealing with a much more complicated geometry in which there might be motion and deformation in different directions, then the relationship would be more complicated than this, but it would maintain that linearity between shear stresses and shear strain rates. It's just that there would be more than one shear strain rate, not just du dy, and there would be more than one shear stress, not just this tau that we define by taking this force and dividing it by the area. But for the time being, this is sufficient for us. So with this simple relationship, we can already try to address some problems. We can, for example, introduce a variation to the problem that we just saw and see how we can use this relationship to obtain a solution. So here is the problem that we can tackle with this information that we have. Suppose that I make the problem a little bit more complicated by adding a third plate. So let's say that I have the bottom plate as before, which is fixed. I have the top plate, which is the one that I am pulling with a certain velocity u. But what I'm going to do now is I'm going to introduce a third plate somewhere in the gap, not necessarily in the middle. Let's say, for example, here a little closer to the bottom plate. And therefore, what I'm going to do is I'm going to put two different fluids in here. I will put a fluid, so this is the third plate. I'm going to put a fluid here in the bottom gap that has a certain viscosity mu, and I'm going to put another fluid up here that will have twice the viscosity. So if this is mu1 and this is mu2, then mu2 will be 2 times mu1. So the fluid that occupies the upper gap is twice as viscous. But this is a solid plate. And I will assume that the two moving plates remain horizontal at all times. And of course, since I am pulling the top plate to the right, the plate will drag the fluid that we call, that has viscosity mu sub 2 to the right, and that will in turn pull the middle plate to the right with some velocity that I don't know. Let's call it v. And I don't know what this velocity is. That's in fact what I'm trying to determine. And of course, that middle plate will move the bottom fluid, mu1. So I'll expect there'll be some motion, but I want to know, for example, determine what this velocity is. Determine v, knowing everything else in the problem. So we also know this vertical distance from bottom to top. Let's call that b. And then from bottom plate to middle plate, this distance we're going to call cb, where c is just a fraction between 0 and 1. Right? So 0 is less than c, which is less than 1. So that allows me to move that middle plate up and down. If I make c very close to 0, then the lower gap is very narrow. If I make c very close to 1, then the upper gap is very small, very narrow. All right, so we'll make some assumptions. We will assume that this is continuously moving. And the way to tackle this problem is by doing a force balance. Remember, we talked about in the first lecture how, let me bring that back here. When we're solving a problem in fluid mechanics, we typically need to satisfy a few physical laws that we are familiar with. Conservation of mass, Newton's second law, first law of thermodynamics, second law of thermodynamics. Of course, the problem that we have with us right now is very simple, and we don't have to look at all of those laws. It is sufficient to look at Newton's second law. The way you can do that is take the middle plate and do a force balance on it. So let's say that I draw here that middle plate, or a portion of it. I cut a segment of it, and I want to do a force balance on this plate. So force balance on middle plate. It's really only a horizontal force balance. That's the only thing I need to worry about, because there is only horizontal motion. There is no vertical motion. So obviously, as we said, the top plate is pulling the top fluid to the right. The top fluid is pulling the plate to the right. So I already know that there has to be a shear stress acting here from the top fluid on the plate. Let's call that tau sub 2. And then, of course, the lower fluid, which is now lagging behind, is producing a shear stress, which is, let's call it tau sub 1. But in the horizontal direction, those are the only two stresses that are acting on the plate. So if I look at the forces, I would multiply times the area. So I know that if I do a force balance in the horizontal direction, what I would have is that tau sub 2 times the area of the plate minus tau sub 1 times the same area of the plate must be equal to 0, because the plate is not accelerating, it's moving with a constant velocity. And therefore, what this means is that the stresses have to be balanced. So I just write tau 1 must be equal, tau 2 must be equal to tau 1. Okay, so, and then of course we know what we just wrote before. And so what I need to do is write expressions for tau sub 2 and for tau sub 1 with what I know about the velocities. Now to this end, it will be helpful to draw the velocity profiles in the fluid. So let me again draw the plates here. And then let's draw the velocity profiles. We know that the top fluid is moving, the top plate is moving with velocity capital U. The middle plate will move with a smaller velocity, which is capital V. And the bottom plate is fixed, so that one is not moving. This is fixed. So if I draw the velocity profiles, they might look something like this. I might have no velocity here, then some velocity until you reach the value of capital V, and then another profile of velocity until I reach the value capital U. Now these two velocity profiles don't have to have the same slope, because of course in fact they shouldn't, because the viscosities are different. But now I can write expressions for the strain rates. So I know that if I do the bottom first, tau sub 1, which is equal to mu sub 1 times du dy, but all I need is then the v velocity divided by the vertical distance, which was cb. Remember, the vertical distance down here is just cb. And then for the other fluid, for the top, tau sub 2 should be mu sub 2. But now, of course, if I want to get that slope, is now u minus v divided by the distance, which is b minus cb, so it will be b times 1 minus c. All right? Because the distance, this distance in this gap is b minus cb. Right? Given that this distance is cb. So I just factor out the b. So those are the expressions for the stresses, and now I just set them equal to each other because I know that's what guarantees a force balance. So I just say tau 1 equals tau 2, and then I can write mu 1 v over cb equals mu 2. But let's go ahead and use the fact that mu 2 is twice mu 1. And then u minus v b 1 minus c is my expression. And of course I notice now that I can cancel out the mu, because it's mu 1 on both sides. I can also cancel out the b that appears on both sides. And what I have there is an expression then that relates v to u and c. And therefore I can solve for v. For example, if you solve then, I'm not going to, this is a simple algebraic solution. If you solve this, you find that v is 2 times c divided by 1 plus c times u. That's our solution. And since, as I said, we knew everything except for the value of capital V, then we can find that that's the velocity of the middle plate. You can verify the limits, as we said, if c is equal to 0, then it's like the lower gap doesn't exist. If c is equal to 0, it's equivalent to bringing the middle plate all the way to the bottom, and therefore, if c is equal to 0, then v is equal to 0. And on the other hand, if you make c equals 1, then you're essentially eliminating the upper gap. You're bringing the middle plate all the way to the top. And that makes this 2 over 2, 1, so it gives you v equals u. So you can verify the two limits as the middle plate moves up or down. So that's a very simple problem using the concept of the shear stress relationship for a Newtonian fluid. Okay, let's talk about units for a second. What are the units of viscosity? We can get them actually from here. So the units of viscosity. By the way, we will learn about another viscosity in a little bit. We refer sometimes to make the distinction between this viscosity and the other one that we're going to learn later. We refer to this as the dynamic viscosity. I'll explain to you why that is in a moment. But when we talk about dynamic viscosity, we're talking about this mu. So what are the units of it? Well, very simple. The units of dynamic viscosity will be the units of shear stress divided by the units of shear strain rate. And the shear stress, of course, has units of force per unit area. So if we are in the international system of units, that would be newtons over meter square. We learned that the shear strain rate has units of 1 over second. So that gives us the units of dynamic viscosity as Newton times second over meter squared. Which can, of course, also be written in a different way, because since we know that a Newton is a kilogram times meter over second squared, then we can plug that in there, and we can say that we can also write the units of dynamic viscosity as, if I plug that in there, I'm left with kilogram. 1 second will cancel 1 second, and the meter, 1 meter will cancel 1 meter, so you end up with kilogram over meter second. And they're equivalent. So these units of dynamic viscosity are equivalent. All right. So I told you there was another viscosity. And the other viscosity we call the kinematic viscosity. Like we call this one dynamic viscosity. We define another quantity called the kinematic viscosity. And kinematic viscosity, we use the symbol nu, Greek letter nu for it, and is defined as the dynamic viscosity divided by the density of the fluid. So we simply take this other viscosity that we call dynamic viscosity divided by the density, and that's called the kinematic viscosity. Which units will it have? Well, obviously, it's going to be units of dynamic viscosity. So let me take, for example, this form, kilogram over meter second. So the units of nu are kilograms over meter second divided by the units of density, kilograms per cubic meter. So simplify, and you're left with meters square per second. And that's the reason for the name kinematic versus dynamic. As you can see, the kinematic viscosity has only kinematic units, length and time, whereas the dynamic viscosity also has the kilogram in it, or the force, if you write it in terms of Newton, and therefore the reason for the name dynamic viscosity and kinematic viscosity. But really what is important is to know that the dynamic viscosity is the constant of proportionality between the stress and the strain rate, and the kinematic viscosity is just the ratio of that dynamic viscosity to the density of the fluid. In many problems, you find out that you end up dividing the dynamic viscosity by the density. Therefore, the kinematic viscosity becomes an important quantity. Let me give you some values just so that you know. Most of the problems that we're going to be working with involve one of these three fluids. As we do examples and so on in the class, we'll do a lot of problems involving air, some problems involving water, some problems involving oil. So it's important to have an idea of what the values of the viscosity, for example, are for these fluids. And these are at the so-called standard atmosphere. So at normal room conditions, 1 atmosphere of pressure, 300 degrees Kelvin. Here you have the viscosity in kilograms over meter second for air, water, and oil. And you can see how they are they get about 2 orders of magnitude larger as you move to the right. So air has a dynamic viscosity which is about 2, 10 to the minus 5 kilograms over meter second. Water, roughly 100 times that, 1, 10 to the minus 3, and then oil, roughly another 100 times. So it is roughly 2 orders of magnitude increase in viscosity as you go from air to water and then to oil. It's important for you to be familiar with other units of dynamic viscosity. You might do problems in which you're using English units. Let me blow that up a little bit. And so if you're dealing with English units, you might encounter viscosities, as long as it is, as you can see, units of mass over units of length and units of time. For example, pound mass divided by a foot and a second, that would be a unit of viscosity in British units. There is a historically important unit in the so-called CGS system. CGS stands, of course, for centimeter, gram, and second. So if you express the mass in grams, the length in centimeters, and the time still in seconds, so gram divided by centimeter and per second, that's called a poise. And it's a classical and still very much used unit of viscosity, denoted simply by P. So a poise is a unit of viscosity. And even perhaps more common is the centipoise. So 1/100th of a poise is a centipoise, CP, 10 to the minus 2 poise. So just units that you might encounter as you are solving problems. Now you may ask yourself, which fluids are Newtonian? In other words, which fluids obey this law? And fortunately, many fluids that we work with as engineers satisfy the Newtonian type of behavior. Most importantly for us, for example, water and air are fluids that behave in the Newtonian model. But there are many other fluids that are not Newtonian. They have different behaviors. Let me show you a movie of such a fluid. And So here is cornstarch. So this is a blob of cornstarch mixed with water. It looks pretty much like a standard pancake as it spreads. But the interesting thing is that if you shear it very rapidly, as you can see this person is doing with that spoon, it behaves differently. Let's look at that again. So right now it seems to be behaving like a Newtonian fluid. It has a certain viscosity that is preventing or slowing down the spread. But you can see how it actually turns almost like into a solid when you shear it very rapidly. So that is a fluid that is like saying that it has a different viscosity depending on the rate at which we are shearing it. So let's do a plot here to illustrate that. Suppose I take and I make a plot of I'm going to make a plot of the shear stress on the vertical axis. So this is tau. And here I'll put the strain rate. In fact, the two quantities that we see are connected by the Newtonian fluid expression. So I'm just plotting tau versus du dy. So obviously it should be very obvious to you what a Newtonian fluid will look like here. And so let's make that, for example, in blue. Since this is a linearly proportional relationship, it has to be a straight line. So a fluid that behaves like that is a Newtonian fluid. And in fact, I can put two different ones. What is the difference between these two fluids? So this is Newtonian. This is also Newtonian. The difference, of course, is the viscosity. So a fluid, the lower slope, measures a fluid that has a lower viscosity. Of course, this slope here, the slope of this angle, is the viscosity, the slope of this line. So this is a fluid with a viscosity, say, mu1. This is a Newtonian fluid with a viscosity mu2, which is greater than mu1. Right? So those are two Newtonian fluids. Any straight line will represent a Newtonian fluid. But what about something like we saw there, the water mixed with the cornstarch, that when you shear it very rapidly, it seems to behave like a solid. So it seems like it has a higher viscosity when it's sheared more rapidly. So that fluid could be represented by a curve that might look like this. Is what we call a shear thickening. A shear thickening fluid. So that's the water and cornstarch mixture. There are other fluids, and this of course is non-Newtonian. Only the blue ones are Newtonian. There are other fluids that do the opposite, that might have a very high resistance to strain when the shear strain is small, but then have a decreased resistance. So these are the so-called shear thinning fluids. So these are both non-Newtonian. So make sure you know that this is non-Newtonian, and so is this, non-Newtonian. Right? Those are two non-Newtonian fluids. Paint, for example, more or less has this type of behavior. It flows more easily as you're spreading it. So if it's thick, it doesn't flow as easily. When you thin it out with the brush, for example, then it flows a little bit more easily. That's a shear thinning fluid. So we are not going to look at these other type of fluids in an introduction to fluid mechanics course. Really all we're going to be looking at is Newtonian fluids, and that will keep us busy enough. All right. There are other properties, so enough about viscosity for now. Sometimes we might be concerned in the compressibility of a fluid. Remember, a fluid can be a gas or a liquid. So what happens when we're dealing with, for example, a gas that can be compressed? Then we might be talking about the compressibility of a fluid, or how to measure that compressibility. Suppose, for example, that you have a gas in a cylinder like we do in thermodynamics, and you compress it. So you apply a pressure, and you're interested in knowing what the effect of that pressure is on the volume. Okay. Pressure, volume. You want to know that connection between pressure and volume. Then you might say that you might want to measure how the pressure changes with the volume. So what is the variation of pressure with volume? And then there is a property that is defined using this quantity, and that property is called the bulk modulus. The bulk modulus, let's call it E sub V, is simply defined as negative volume times dP dV. And that's a way to measure compressibility. The negative sign, of course, is because since typically higher pressures, if you increase the pressure, you'll reduce the volume, or if you increase the volume, you'll reduce the pressure. Typically, this quantity will be negative, and therefore the negative sign makes the property bulk modulus be a positive property. Okay, so let's end it here, and in the next lecture, I'll say a few more things about other properties, and then we'll start talking about hydrostatics.